Okay. Thanks for having me. And it's a pleasure to be here to talk a little bit about molecular dynamics and also about the GPU, how GPU is important for molecular dynamics. There is some structures, molecular structures that you have been working for a long time. You have here protein, main protein. You have also here is biodiesel. I don't know how to say that. We're going to talk in, I split the presentation, the lecture in three parts. The first one, I'll talk a little bit about molecular dynamics simulations, how the things work, only for you all have some idea about that. Okay. I'm not sure how to do that in computer, but I'll show you the electrical base or something. We are going to talk about the GPU performance for molecular dynamics simulations. Use the Amber Softpack. So Amber Softpack, I have been working with Amber Softpack since 2011. And by the way, Ricardo told you about my postdoc at University of Florida. And I went there to work about some kind of special simulations. And I'll talk about that in the last section. In these last sections, we'll talk about a special kind of simulation that you can set the pH for your where your biological system is, and also the electrochemical potential. So, and there is some issues we have when I need to get this parameter there is delta G reference. So I'll talk a little bit, maybe you guys can help me to some ideas to do that. Okay. Okay, before start about the base of molecular dynamics, I will show you something that is really important to understand how we are working. In the screen, you can have the pictures from websites called PDB, the Protein Data Bank. In that website, you can get information about the experimental results, mainly experimental results for structures of protein and protein binding with ligands and a lot of biological systems. So if you want to start to study some protein, you need to go there to get your 3D structure for your protein. Oh, by the way, focus this presentation mainly in the study of proteins. Okay, you can have a lot of kind of system to study. So here, this is information about the crystal structures of human base 1 in complex with a ligand compound. Okay. You can see that these results, they got this information from experimental and using the method X-ray diffractions. So this is what I have. With that information, you can get what you can see in the screen. Oh, I should use that. Yeah. Here is all the protein, the secondary structures, and here in the middle is the ligand, okay? And how you all can see the ligand is binding to protein. It is really important to study new drugs using molecular dynamics or molecular modeling in general. Another kind of information you can get is the interaction between the protein and ligand. This is really important. Here you have acid aspartic, and in the left here you have also acid aspartic, and we have some residues from protein here and here. And in the middle you have our ligand. This ligand is called D9W. I don't know why, but yeah. And you can see here 8 bound interactions, mainly in that place. Okay, this region, and here in green you have hydrophobic interaction. So without molecular dynamics, you can get the information in that website. So yeah, so this you have attention that you have pictures of the protein in the ligand binded in the protein. Okay, this is really good. Oh, by the way, the base 1 is one of target protein to develop new drugs for Alzheimer. It doesn't mean that D9W is a candidate. It was tried to be, but it's not good enough to be a new drug for Alzheimer's disease. Okay. Here in this slide, we will have results from molecular dynamic simulations. And one of kind of formations that you have, hope that you are all seeing the movie. The molecular dynamics create a kind of movie of all atoms that can change during simulation. So they can change the position, and you see in the next slides, and change the velocity, and also, this is important, can change the that interactions between ligand and protein. Okay. This is also in blue is the base 1 protein, and here in the middle, this is a point that is very important to understand how powerful could be the molecular dynamics. I'm not, in this movie, I'm not showing that ligand that I show in the previous slide. I'm showing another one. And this another one is the MK8931. Is this complex? Okay. This is molecule. Here is D9W, but this is so the point here is that I can get that information from the PDB site, and for example, I can change the ligand and put another one that I want to try to see the interactions with the protein. So, and by the way, this compound MK coming from Merck, the pharmaceutical industry, and they were trying this compound to be a new drug, but there's some problems in the preclinical stage, and sorry, it is not be MK will not be a new drug, unfortunately. So anyway, I can study the interactions with the protein and try to change something in some atoms or some kind of functional group to get the best interaction with protein. Okay. So in molecular dynamics, I can have some kind of movement, and I can see, actually, I can see the movie, and this move, when you get information, you call trajectory of our molecular dynamics. And the trajectory of our molecular dynamics means that you have the coordinations that the system is getting after time, after any step of molecular simulation. Okay? So, talk a little bit about the idea, the main idea of molecular dynamics. Initially, you need to have information. The first very important information is about the position of the atoms. For protein, you can get that website. Or if the website doesn't have the protein that you want to study, you need to try a different way to do that. So, but I'm not going to talk about that here. So another way that I will talk in the almost in the end of presentation, I will talk about the input generator website. Okay. So another information that you need is the potential interaction. This is really important, how the atoms will interact with each other, how they could interaction. So, and this point, I need to choose a force field, the force field and parameters for that force field. Force field basically is a question that can get the potential interactions between all atoms in the system. Okay. The next step. Oh, by the way, I didn't say about the velocity. In general, actually you don't need velocity because you start in our simulation in 0 Kelvin. In 0 Kelvin, the velocities of all atoms are 0. So you start in 0 Kelvin, and after that you start to eat the system, eat the system till our target temperature. So suppose that, okay, I need to study my system to 300 Kelvin. So I need to eat the system to that. When our system be in 300 kelvins, of course, our atoms will have velocities. All atoms will have velocities. This is the basic of thermodynamics. So after that, you can start our simulation, and to start our simulation, you need to compute force of the atoms interactions. So, and you use that, the physics 1, that you have for all course in university, most of course, of course. And you can calculate the force for each atom using this equation. The second step is, if I know the force for Newton's second law, I can have the acceleration. And this is, of course, this is the Newton's second law. And here is another way to write that. And if I have the acceleration, it's about kinetics. If I have acceleration, I can get the velocity, I can get the positions, and so on. Okay. And after that, I need to save information on disk. So we call that a snapshot. So you can save information, positions, velocities, energy, temperature, pressure, and other kind of information. So you need to save in disk, in your hard disk. Okay. So this is the basic of molecular dynamics. And after that, here you can get in step 3, you can get the new positions, new velocities. And after that, the saving disk, sometimes saving disk, I need to calculate again the new force because the position change, and I go again to calculate the accelerations and the cycle. This is the main idea. Okay, next slide. This slide, I'm talking a little bit about step 3. This step 3 is the way that they get information about the new velocities and the new positions. There is a typical protocol when you use the algorithm, integration algorithm called Leapfrog. I'm not explaining about his name now, but the idea is pretty simple. The new velocity you get from your velocity that you have, and you can need to have the force, and you have the mass, and you have delta t. This delta t is called integration time. This is very important parameter. Okay, so using this, I can get the new velocities for all atoms in the system, and after that, in this step, I can get the new positions. I get the positions that I have, and I have the new velocity here that I get in this first equation, and delta t. In general, in the most simulation of protein, you have the integration time in 2 femtoseconds. That is really small time. Femtoseconds is 10 to minus 15. Yeah, I think so. But it's, yeah, it's short time. Okay. So in the step 4, you need to save information in the disk. This is you are creating your file called trajectory that you have all coordinates from all steps. But it's really complicated to save each 2 femtoseconds, save a lot of coordinates. So, and also you don't need to have all this information. So usually you save information in disk every 2 nanoseconds. So it means that, I save information in the hard disk each 100 steps, 1,000 steps, okay? So this is enough because I will have the trajectory and I will analyze statistically later. And how I told in the previous slides, I save this kind of information, including that one of protonation states and redox states, right? Yeah. Talk a little bit about force field. The force field, there's 2 main components. You have the functions, all functions that we use for describe different kind of interactions. And you have also the parameters for these functions. And I'm showing some situations. This is the way that a force field can deal with the oscillations between 2 atoms, oscillations in the bound between 2 atoms. Here you talk about interactions for atoms that are covalent bound, okay? Basically, we have like a spring movement. When you have a spring, you have 2 parameters in yellow here. And this one is about how the string is hard or not. So, for example, if you have a carbon and carbon, a string between these atoms, you have a kind of springs. If you change a carbon and a hydrogen, or carbon and oxygen, you have a different spring. Okay? So this information you need to have to run molecular dynamics simulations. And also all the information about springs is the equilibrium position. That is B. Okay. Yeah. So basically is that. There's other kinds of bond corrections. Here showing we have 3 atoms. So is also described by Hooke's law. So this spin describes the spin movement. You need also a function to describe the rotations of chemical bond. So they happen in the real system. So you need to have some expressions to do that. So here is the expressions, and you can use it. It's not more about spring movement, but yeah, it's a same cosine functions. There is also some atoms not are bounded together. So, for example, if you have a protein, you have a lot of atoms, and they are not covalent bind to waters. So the interactions between that atoms with proteins, inside the proteins with waters, are by no bounded interactions. In our case, learning joins and Coulomb potential. Okay. This is only for some ideas. Here you have some results, 2 graphics that in all simulation you need to see, you need to analyze. It's pretty simple. In the left graphic, you have both are in function of time, and here you have potential or energy per atoms. This is very important to know if your system is in the thermodynamics equilibrium. So this is really important because you need only to analyze that situations. In most situations, you have our system in thermodynamics equilibrium. And here is also important temperature in function of time. So this is in the beginning of here. You have that, you can see that the temperature increase very fast, actually very fast. And when the temperature gets the target temperature, 300 kelvins, they keep almost constant. So this is one of the graphics that you need to see, but there's a lot of graphics that you can get from molecular dynamics, and you need to analyze too. Okay. Okay, now we are going to talk a little bit about the performance of the GPU for this kind of simulations. And we are talking about the information that I got on internet in the Umber website about the GPU performance, or you have GPU benchmarks. Okay. And for that, I choose 2 biological systems. The first one in the left it's pretty difficult to understand the pictures, and yeah, but I know that it's a collection of proteins in water. Probably you are not seeing waters, so you can see only the fibers. Okay? These systems has more than 1 million atoms. So it's a lot. For sure, it's a lot of atoms. So, but the point is that you can do that. You can study a virus. It's not simple, but it's possible. In the lab on the right, you have a protein with more than 20,000 atoms. So it's not too small, but it's a small protein. Okay. In water, it's also possible to see the water here. And here you have some information about the GPU performance. Basically, I would like to say the yellow GPU, because it's the most similar GPU that you have in your lab. You have around 10 GPUs. Is not so good with the yellow GPU there, but the performance is almost the same. Our GPU in the lab is a little bit present a little bit worse results, worse performance, a little bit. So, and another GPU that I would like to compare, I don't know why it's showing, but hang on. It's difficult to. Are you guys seeing what I'm seeing in my screen? There's options here. I don't know.
So Marcos, we're seeing a toolbar below the slides there.
Yeah, there's options here to leave the presentations or yeah, okay. I'm trying to okay, I'm not going to that way. Last month we submit a project for COVID virus, and it's a project that's pretty simple to simulate some one of the possible protein for this virus. So, and now you can buy that green GPU, only one, unfortunately, and the money was not possible to buy the GPU tie Y below. Okay, but yeah, so this is what you have. And also important here is compared for the performance. Oh, by the way, the performance you use to see how much or how many nanoseconds per day you can have with simulations. Okay, so here you have the nanoseconds. For CPUs with 36 cores, to simulate the virus, the performance is almost 2 nanoseconds per day. And in our GPU, the yellow one, you can go to almost 8 nanoseconds per day. So the performance is better, almost 7 times faster. So this is really good. If suppose that our simulation is for 20 nanoseconds, so in CPUs with 36 cores, I will need to wait for 12 days. And in GPU, you need to wait less than 3 days. So this is really good. For our new GPU card, the performance is much better. You can get almost to 18 nanoseconds per day, and you need only to wait for 1 day to get the virus simulations for 20 nanoseconds. Remember that each step is, in this case, each step is for 4 femtoseconds. So you have a trick to do that, but so you can see that the performance is much better. And also for this protein, of course, you can get more nanoseconds per day, and the performance you can get almost 8 nanoseconds per day in GPUs, and almost 400 nanoseconds per day in your or yellow GPU. And here for days, suppose that you need to run 200 nanoseconds. And for 200 nanoseconds, you need to, for CPUs, you need to wait almost 3 days. And in GPU, you only need to wait for almost 12 hours. Okay? And for green GPU, you can have, you can get almost 800 nanoseconds per second, and you can get our results in some hours. So this is really good. Okay. One point is very important to talk here is that not the point that, okay, I can run in CPUs and wait 2 weeks, there's no problem. I don't know, but I don't need, of course, everyone would like to have the results very fast. But in GPU, you can get in less than 3 days, in this case of virus. But the point is that usually you need to run a lot of simulations in the same biological system. So this is the point. So it's not only one simulation. You need to try simulations. You need to see if your parameters were right, and if the parameters are giving good results, or there's a lot of things, and probably more than one simulation. Okay. Here I got the kind of, here in this graphic, I get a little, suppose on simulations a little bit different. Suppose that I need to try to run a simulation for this virus for 1 microseconds or 1000 nanoseconds. And I need to test for 2 temperatures. For COVID, some discussions on internet is about the virus can survive in low temperatures, not in high temperatures. So suppose this is our virus, suppose this is our COVID virus. So I need to test at least in 2 temperatures, and maybe for 1 microseconds. So what you have here is that in CPUs, I need to wait for 40 months to get these results. In GPU, in the yellow one for our lab, you can wait only for almost 5 months. So that's a lot of time. And the new one that we are going to buy, the green one, is you can wait for less than 4 months. And that one is less than 3 months. So it's, in this case of CPU, it's not possible to have, this is not for master degree students, right? More than, yeah, more than two. Maybe for PhD students, it's not possible to study this kind of system because you need to read so long. Okay, so I also went to internet to get the specifications of the yellow GPU and the green GPU cards, and this is what I get. This is the simple one. I, for sure, to be honest, I have few ideas about that, but let's see what we have here. The Bose clock, I have no idea what is that, but the frequency here is high. The memory clock is also, wow, the double here. CUDA cores is almost the same. And you have different memory, not only in the size, but of the I don't know how can say that, but they are different, 5 and 6. And you have another information here. So this is maybe this kind of information that you guys could help me to understand what's really important in the GPU to improve the performance. That unfortunately you don't have money to buy it. There's some better GPUs than these two GPU cards, but yeah. So this is kind of information that I got. So the last topic we are talking about is the kind of challenge that you have to run constant pH and also constant electrochemical potential. I would like to talk a little bit about constant pH, this kind of simulation. In this kind of simulation, you need to choose the pH. For example, oh, my protein is on my broth in my body, okay? And the pH for my body is, of course, not the, I don't know what to say, but is 7.4. So I can choose that before I start the simulation, and some residues of proteins can change the protonation state during the simulation. This is not common. So you need to run this kind of simulation to change. What that means? It means that in this picture, you have aspartic acid. Suppose it is the protonate. So it means that the aspartic acid can gain one proton or keeping the protonation. The protonation is, of course, is not proton in the aspartic acid. So during simulation, there is a probability to be accept the change of the protonation state. And to do that, you need to use these expressions here, and you need to calculate delta G, okay? The delta G, the equation is that one. It's Boston constant temperature, the pH that I said in the beginning. pKa half is the pKa for aspartic acid is 4.6, I think, around 4.6. And something here. And during the simulation, the Ampere will calculate the delta G electron. So every time they try to change the protonation state, you need to calculate that. But the point is delta G electron reference. This value I need to have before start simulation of my protein. Okay. So, of course, the aspartic acid, it has in a lot of proteins. So this information, this value for delta G electron reference is implemented in the Umber software. So if I need to study a different compound, maybe I need to find this parameter. So, and for do that, I need to get the aspartic acid alone in water and try to fit the protonation curve. So there's the main idea here, I'll talk in the next slide too, is I need to get this aspartic acid simulation in water, shows pH the same for pKa for this aspartic acid is 4.6. So when I set, when the pKa is the same of, oh, sorry, the pH is the same of pKa, during simulation, the aspartic acid will be half of time deprotonate, like that, deprotonate without protons, and half of time protonate. So this is for definition of pKa. If you have pH, it's the same of pKa, you have the system changing a lot of time, but in the end of the day, you have the half the protonate and half protonate. Okay. So this is one thing that we need to do when that simulation, that's kind. So what is important, because you know the pKa for aspartic acid. Here in the picture, you have the aspartic acid here, and here is our D9W ligand. Oh, here you have the base 1. So when the aspartic acid is inside the protein, the pKa of this aspartic acid change because the environment around it is changed. You have charge here. So this is a good way to have the correct interactions between your protein, mainly in aspartic acid with the ligand. So this is one of the reasons that you need to do that. Okay. Now I'm going to switch to constant electrochemical molecular dynamics. It's almost the same thing, but the constant pH, you are talking about lost or gain proton, and electrochemical, you have to gain electron or lost an electron. Okay, so the equations is basically the same. You have the same situation and the same way to calculate the probability to be accepted. Suppose you have your, in that case, you have your iron 3+. So you try to know if can change the state, can reduce, can lost, can gain an electron, okay? Or if the iron is 2+, how to gain electron, to lose electron, actually. So we will also have, similar to pK8, is I8, actually I12, and here's electrochemical potential. We will also set shows in the beginning of simulation, and F is a Faraday's constant. Okay, so for this process, redox process, the pKa for iron is 0.770 millivolts. So what we need to do for it, this is each point here means that I need to run one simulation. So I need to run the simulation here with electrochemical around 0.65, and I need to run a lot of simulations. You know how GPU can be important for that. It's a lot. For these systems, it's only the iron atom, so it's really quick. I can run CPU in this case. And here, the information is about the fraction reduced. So, for example, if this is information here means that the most part of all simulations, the fractions is close to 100%. So our systems is in the iron 2+. And here is opposed that most part of time, almost all time, the fraction reduced is close to 0. Okay. So, and here is really important. The half of time the iron will be in reduced state, and half of time it will be in the oxidation state. So will have a electron or not. So okay, so almost settled. Okay, for iron atom it's pretty simple. I did that, and it's a really good exercise for new students on my lab. But recently we are studying with undergraduate student the cytochrome C. And cytochrome C, you have this structure here, is the heme structure, and in the middle you have an iron atom. But for this system, you need to run this protein with a heme system in the middle, and the pKa for the system, or electrochemical half, is 0.248 millivolts. Okay, so you need to run again. You need to run to build this electrochemical curve, but it's not so simple. Of course, there's a lot of atom, and to run that, and here you really need GPUs. Okay, so how can we do that summarily, or speaking a few words? You need to get the charges for both reduced and oxidate, and this is our problem: is get the delta G electron reference for redox state. If I do not have this parameter, it's impossible to run a constant electrochemical molecular dynamics. So it's impossible to have during my simulation this redox reduction. And this is really important to have. So how calculate the delta G electron reference? One of the ideas is like I did for iron. So I need to choose one electrochemical and run. I need to choose another one, and I need to, no, I don't need to choose difference. Actually, I need to choose one value. I need to choose this value for the electrochemical potential and run the simulation and try to get 50% of reduced states and 50% of dice states. But I needed to try some values for delta G electroreference. So I try anyone. And of course, in first try, I not get the 50% that I want. So I need to try another one, and I need to try another one, until get the 50%. So in general, I have been trying. You don't have a good code for that. This is the point. So it should be very interesting to have a code that can get your system. In that case, the cytochrome C can calculate the charge, can try to discover or try to fit the delta G electron reference, and provide this information so you can start the real simulations of the cytochrome C. Okay. So probably this is almost the last one, the last slides. Here are some open ideas that I would like to share with you guys. The PacMol is very useful software that you can build initial configurations. You need some years ago, you need to build a system with different alcohol. Suppose that I want to simulate, for example, I want to simulate a mixture between ethanol and methanol. So a good way to do that is using PacMol. And they can prepare your system. They can prepare different system for that. So it's very useful for those people that need to study some new biological system. And in general, this, for example, in my lab, I have some students for biological course, and some students, not all, but they don't know how to use thinking about some software to prepare their systems. So it's very useful when you have something like that. And another one, I have students, PhD students that work on kind of simulation, or kind of project that you build a website that can help you and help other people around the world that want to have input generator. You have something that can help to generate the input files. And the input files, like I said in the beginning, is that provide you the coordinates of our system. So you have also study of membranes and the proteins in membranes. And one of my collaborators, Sergio, used this website to build our biological system with membrane. Okay, so it will be very useful to have a kind of website that can deal with constant pH, constant electrochemical. So it's only necessary to provide information for our system and get all parameters that we need. So these are teams of collaboration. Danilo is from Federal University of Tocantins. Sergio is postdoc from CDB. Marcos Vinicius work with biodiesel, and our lab, I don't know, say English, but Rodrigo is help us or our system, or your configuration, or our GPU. And there's some students there. The first line is a PhD students. The second line is the master degree students. And of course, the last line is undergraduate students. And yeah, and yeah, it's that. Thank you.